So for the rest of today, what I'm going to do is just basically a whirlwind review of a mathematical concept they're going to be using over and over again because we use it to describe phenomena in 3 dimensions, and electric and magnetic interactions are inherently 3-dimensional. And that is vectors, okay? We've all seen a vector before, yes? Anybody not seen a vector before? Okay, good. What's a vector? A vector has a direction and a magnitude, okay. So graphically, we can represent a vector with an arrow. An arrow looks good because we can have a length of an arrow giving us the magnitude and the direction giving us the direction. So if we have a coordinate system, Cartesian coordinate system, where positive y is up, positive x is out towards us, and positive x is to the right, and positive z is out towards us, then we could represent, for example, a position vector. If this is our origin here, and we wanted the position of some object with respect to that origin, let's call it position vector r, and give it, well, in general, it has an x, y, and z component. So if you didn't take the M version of the course last semester, just be aware that this is the notation we're going to be using for vectors, just this angle brackets with a triple notation, components separated by commas. It's equivalent to writing r sub x I hat plus r sub y j hat plus r sub z k hat. Okay? So equivalent ideas, but this is the notation we're going to be sticking with. So if I have a vector, for example, 4, 3, 5, so it's a position vector, 4, 3, 5 meters. I'm talking about something that has components. So let's draw this in a different color. And the components, 4 meters in the x direction, 3 meters in the y direction, and 1, 2, 3. Let me extend this out a little bit. 4, 5 meters in the z direction. And then you can think about a 3D vector just being an arrow that extends from one corner of a box that is bounded by these sides given by the components. And that's a little tough to draw. So the vector would extend from the origin to that corner. Okay, a little tough to draw in 3D, but you get the basic idea. What can we do with vectors? Well, how do we find the length of the vector, the magnitude? It's been a long break, right? Square root, sum of the squares of all the components, right? R sub x squared plus r sub y squared plus r sub z squared. Okay, so just to wake us all up and get our brains going again, try finding the magnitude of 435 meters, okay? And then you should bring a scientific calculator to class every day because we are going to be doing calculations in class. So real quick, real simple, everybody take out a calculator, just find the magnitude of this vector 435. .07. 7.07, and it has units just as the position vector have of meters, right? We agree? Yes? Okay. Can a magnitude ever be a negative number? No. Okay. What can we do with vectors? We can do various types of operations. We can do vector addition. You have two vectors. Let's say R1 is equal to what? Say R1 is equal to 4, 2, 0. R2 is equal to negative 2, 3, 0. And these are, say they're still position vectors. And I want to find R1 plus R2. I add two vectors by just doing what? Adding the components, right? Okay, so we're going to get 4 plus a negative 2 is 2. 2 plus 3 is 5. And 0 plus 0 is 0. Graphically, vector addition means what? What are we doing graphically when we're adding two vectors? Tip to tail, right? So if you place them tip to tail, let's draw these out. So I'm just going to draw the y and x directions here. And if I have 4, 2, 0, so that's 1, 2, 3, 4, and 1, 2 units, so that is vector R1. And if I place vector 2, the tail of vector 2 at the tip of vector 1, vector R1, which I can do, I don't have to draw these vectors all stemming from the origin. So if I do that, I start here at the tip or head of R1, and I go 1, 2 units, 2 meters in the negative x direction, and then 1, 2, 3, somewhere up there, right? 3 units in the positive y direction, so 1, 2, 3, somewhere up here. That would be R2. And then I just draw the vector from the tail of R1 to the tip of R2, which is a vector that looks like this. That's R1 plus R2. Let's see, it looks like it has x component of 2 and a y component of 1, 2, 3, 4, 5. Okay, so tip to tail, graphically, that's what we're doing by adding vectors. You could also have drawn R2 at the origin, with its base at the origin. So 2 units in the negative x direction, 3 in the positive y. And then you can think of drawing a parallelogram where R2 and R1 make up the sides of the parallelogram, and then R1 plus R2, the sum, just extends from one corner to the other. Okay. We've all seen this before, right? This is nothing new. What about vector subtraction? If I say R1 minus R2, I just subtract components, right? So that's going to give me 4 minus a minus 2 is 6. 2 minus 3 is negative 1. And 0 minus 0 is 0. Okay. What's the physical or geometric interpretation of vector subtraction? Where have you seen that before? Okay, a delta, right? A change or a displacement or a difference from one position to another. So graphically, what would I draw here? A vector that points from where to where? It's final minus initial, right? So we can think of this, if I call this R3, we can say that this is final minus initial. This is sometimes called a relative position. Vector. So final minus initial, it's pointing from where to where in this case? Where should the tail of the vector be? Okay, let's clean the picture up. Let's say I have just these two vectors, R1 and R2. Anybody know? Okay, it starts at the R2, right? And it points to R1. Oh, that didn't go too well. Let's try that again. Something a bit more straight. Going something like that. Okay, so that's R3 is equal to R1 minus R2. how can we check that? Well, let's check it by adding the vectors up. We can rearrange this and say that R1 is equal to R2 plus R3, right? Well, look what we're doing. We're adding these two vectors together. We're saying R2 goes from the origin to here. Add tip to tail R2 and R3. R2 plus R3 gives us back a vector that points from the origin to this final point. That's R1, okay? Why is this important? Because we're going to be looking at, especially when we're dealing with how to calculate fields and forces, how to find a vector, a displacement vector or a position vector that points from one location in space to another. Okay, so for example, if I had a proton here and an electron here, this relative position vector is giving me the position of the electron relative to the proton, or with respect to the proton, okay? And that'll be important soon. We'll be dealing with how to use this to calculate fields, okay? Questions here? Is this okay? Is this, people have seen this before? Yes, no? Kind of, okay. All right. What else can we do with vectors? We can do a scalar multiplication. So what do I do when I multiply a vector by a scalar? What do? What happens? Okay, you have a new vector, right? And what do I do to the components? So if I have, say, s times vector r, where s is a scalar, then what are the components of this vector? S times rx, s times ry, s times rz, okay? The new vector is, how does the direction relate to of this new vector compared to just r? So if I multiply by a positive scalar, I get a vector that is in the same direction, right? So if this were 5 times r, I get a vector that is in the same direction as r, just 5 times larger, right? 5 times bigger magnitude. What if I wanted a vector in the opposite direction? What do? Multiply by a negative scalar. Okay, so negative 1/2 r compared to r would be in the opposite direction, and its magnitude would be half the size, right? Half as much as r. Okay. Nothing too tricky about that. So just as an example, if you have, say, r1 is equal to, again, 420. If we wanted a new vector that was in the opposite direction and 1/4 as large as r1, I would negative 1/4, right? So negative 1/4 r1 is 1. 2/4 is 1/2, or 0.50. Okay, and you could plot that just to verify. So if this is 1, 2, 3, 4, 1, 2, that's r1. Then this is 1 unit and 1/2 a unit, so something like that. That's negative 1/2 or negative 1/4 r1. Okay. What if I want a vector that points in the direction of r1 but has a length of exactly 1? What's that called? That's a unit vector. To make a unit vector, what do? Divide it by the magnitude. All right. So we say that a unit vector, the notation we use is this hat notation. So a vector has a little arrow over the top. And these little symbols are very important, right? It's very important that you actually draw the little arrow symbol over vector quantities and don't draw it over scalar quantities, okay? Because it actually has important meaning, important communicative value when you're writing out solutions and so forth. And so this little hat symbol indicates a unit vector, and it's defined to be, in fact, I'll just call it r hat, the vector divided by its own magnitude, right? So in other words, more spelled out, we take the component, the x component, and divide it by the magnitude, rx squared plus ry squared plus rc squared, square root. And do the same for the y. Okay, I won't write it all out, but do the same thing for the y component. Do the same thing for the z component, etc. Okay? So let's try it. What's the unit vector r1 hat that points in the direction, again, let's say r1 is 420. Take out a calculator, see if you can figure out the unit vector in the same direction as 420. Anybody have it yet? Anybody find the magnitude of R1 first? That's the first thing you have to do, right? So what's the magnitude? Square root of 20, which is something less than 5, right? 4.47, okay? So the x component would be 4 divided by 4.47, or 0.89. Okay, y component is going to be 2 divided by 4.47. That's 0.447. And then 0 divided by the magnitude is just 0. Okay? So you could try it. If I take the magnitude of R1 hat, if I take the square root of 0.89 squared plus 0.447 squared plus 0 squared, I should get back, what should it work out to be? At least close to 1, right? Okay, and you can try that out and verify that. Why is the unit vector important? What do we need it for? Okay, creates a direction. The unit vector gives us basically pure direction information only. Okay. Anybody? Where? Those of you who took 205M, where have you seen it before? Where did we use it last semester? Okay, gravitational forces. It was used, right? Because in a gravitational force, you had a vector, a relative position vector from, say, a star and a planet. And if you defined a relative position vector, call it r, pointing from one object to another, you know that the force was in that, really the opposite direction, so we had to multiply by a negative sign. If we're looking at the force on the planet, the force would be that way. And so you had a negative sign to give you the correct direction. The magnitude was g m1 m2 over the distance squared. But that's only a scalar part. To give you the correct direction, which has got to be opposite to this r, you got to multiply by r hat. And we're going to be seeing a similar use starting on Wednesday when we're dealing with electric fields. When we have a separation between two points in space, or between a charge and a point in space, we want to use unit vectors to give us the direction and then multiply by an appropriate scalar so that we can scale the vector to be the appropriate size that we want. Okay? Questions? So that was our sort of whirlwind, quickie review of vectors. Anything not familiar to people? Everybody's seen all this before? This all looks good? Anybody have the clickers today? Oh, several of you. Okay, well, let's try a couple questions. So let's try this question. You have a proton at 0, 3, negative 2 meters, an electron at location negative 1, 0, negative 6 meters. What's the relative position vector from the proton to the electron? From the proton to the electron. There are some choices for you. Let's see if we can try this out. Okay, so most of us have got this. It is going to be what minus what? Final minus initial, so the final location is the electron, right? So the r vector is going to be the position of the electron minus the position of the proton, or 1, 0, or excuse me, negative 0, negative 1, 0, negative 6 meters minus 0, 3, negative 2 meters, which gives us answer number 2, negative 1, negative 3, negative 4 meters. Okay? Not a problem there. All right. Let's try another one. Oops. Unit vector in the direction of 3, 5, negative 2. Let's try that. You can always do this one just by guessing, right? Hardly have to do any calculation here. Let's see what we got. Okay, number 4, right, obviously. Is 2 a unit vector? No, the magnitude of that thing is not 1, right? The components might be 1, but the magnitude is going to be square root of 3, right? So, and you can test the other one. This is just the vector itself, and that one doesn't work out. And you can just, you see that this one has the correct signs of the components, right? The unit vector has got to be in the same direction as the original vector. So it's got to be answer number 4, okay? Questions? Okay, on Wednesday we will actually start some fun stuff.